See, so today's class will be for the control structure of UPFC. So how do we control? So UPFC, the control structure will be a combination of that series and then shunt. So state comp and triple SC. Okay, so since it is a combination to two, so it will have shunt control and then series control both. So control structure will be. So control structure of this one. So now the thing is, now we have considered that we have been discussing that, saying that the UPFC has a unique character, right? Unique characteristics. That is, it has the ability to inject the AC compensating voltage with an arbitrary magnitude and angle in series with the line upon common, subject only to the equipment rating. Otherwise, the only disadvantage is subjected to the equipment rating only. This is the only limit which the UPFC is actually limited by doing. Otherwise, it has the superior operating characteristics because of its ability to inject the inject. Other factors will not actually limits is injecting AC compensating voltage. Only the limitation here is the equipment rating. So that is the only. So that is your design drawback. That is. Otherwise, like UPFC has the superior or the advantages, superior operating characteristics compared to STATCOM, compared to triple SC and other facts controller. Then another point you can have is, with the suitable electronics control, UPFC can cause the series injected voltage vector to. So here with suitable control like diode or thyristor, whatever maybe you can use this to make it rapidly, very rapidly and continuously in magnitude or angle as desired. So as and when you, so you can control it. Okay, so both in magnitude as well as in angle as per our requirement. So therefore, it is not only able to establish our operating point within a wide range of possible PQ condition on the line, but also it has, so not only this, so we have seen this circular, that it has the inherent capability to transition rapidly from one such achievable operating point to any other. So that is the disadvantage of that UPFC. Then the control of UPFC is based upon the vectoral control approach, similar to the triple SC and that one. And in this section, we are using the term vector. Why? Because it represents a set of three instantaneous phase variable, voltage or current, that sums to zero, means that is balanced load. So in balanced load, what you have, so like suppose if load is set balance IR, when do you say balance load? Plus IY plus RYB. IB is equal to 0. Okay, so then we say
Zero.
it is balance load. So balance, then that is what. So this is what you saw. This is, so that is why we call it as vector instead of phasor. Then the symbol, this symbol V and I are used for voltage and current vectors. So here in this control stage, we will be using these two symbols, V and then vectors. So we have this. Okay. Then as we know that these vectors, this current vector and voltage vectors, are not stationary but moves around a fixed point in the plane as the value of phase variable change, describing the various trajectories or that path which becomes circle. So that we have seen, no, in circle we used to have that, because like say suppose here we have Vs, this is your Vr, then this is your Vs. So now when you are injecting VPQ, say suppose VPQ in this side, Then this is your V1 PQ, so compensated voltage or injected voltage. Then this one will be your Vx1, so V1x. So this is what voltage across the inductor. Then with this as a radius, V1 PQ as radius and center here, then it used to have this circle. So this circle. So this is what it is actually. So it varies there. So phasor obtained phasor, okay, so which becomes circle. So this were identical to those obtained with phasor when the phase phasor represents a balanced steady state condition. So this is now for the purpose of power control. So controlling the power flow, it is useful to view this vector in an orthogonal coordinate system with P and Q axis, such that P axis is always constant with the instantaneous voltage vector and Q axis is quadrature with V. Means you can have this PQC, that is what we have. In this coordinate system, P axis current component IP accounts for instantaneous real power and Q axis current component IQ for reactive power. So same thing, yeah, IP is for real power and then IQ for reactive power component. Then under the balanced steady state condition, P axis and Q axis components of voltage and current vectors are constant quantities. So during the balanced state. And these characteristics of the described vector representation makes it highly suitable. So for the control of UPFC by facilitating the decoupled control of real and reactive components. So you can have that decoupled. So now if you see, this is what just a brief introductory part of control structure. Now, as discussed in the STATCOM and then triple SC, UPFC control can be divided into internal or converter. So the controlling of converter section and external or functional operation control. So two. Okay, so we have internal control and then external control. Then if you go to that internal control, the internal control operates the two converter, okay, so two converters, so as to produce the commanded series injected voltage and simultaneously draw the desired shunt reactive current. So this is internally. The internal control provides gating signal to the converter wire so that the converter output voltage will be properly respond to the internal reference variable IP ref, IQ ref, VPQ ref in accordance with the basic control. So here. So this is your basic control. So here you have internal. This is you are controlling actually this. You are giving V reference from this shunt 1, shunt 2 UPFC. Then you are giving the reference this references to the shunt converter, and then you can have this. And then series controller, you have series. So it's a combination of it. Then the after getting all this thing, what you will get is you will be giving to the controller. Okay, so this controller converter get signal of the converter, and then it will be injected to the line. So P and Q is how it is controlling. Here another point, you have the series inverter or converter responds directly and independent to the demand of series voltage vector index. So it is independent of, so series converter actually series that triple SC is independent of the demand for series voltage induction, that is VPQ. So it is independent of VPQ. Then shunt converter we have to, so operates under a closed loop current control structure whereby the shunt real and reactive power components are independently controlled. So there, so shunt real and reactive power are controlled independently, not dependently one another. Here the shunt real power is dictated by another control loop that acts to maintain a preset value level on DC link. Okay, so here shunt is actually controlled by another loops X to maintain the preset voltage level here. So before that VDC you are giving. So that is what it is. So this, so shunt rail power is dictated by another control loop. So this control loop. Okay, so this is what we have. Then another one here you have is the external or functional operation of the control defines the functional operating mode of UPFC. So functional operating mode of UPFC, this is, and is responsible for generating the internal references. So the external or functional operation actually is responsible for generating the internal references variable VPQ ref and IQ ref. So here it will be there, VPQ ref and IPQ ref. So this part is internal. So this actually is required for generation of this VPQ ref and then IQ ref. So IQ ref somewhere else here. Okay, so this IQ ref, it is responsible for this. So either way, shunt nadi IQ way. Okay, so then the functioning operating modes and demands actually. So same thing. So you are control discharge. So as shown in this figure, uh, the capability of unrestricted series voltage induction together with independently controllable reactive power exchange offered by the circuit structure of two back-to-back converter facilitates several operating and control modes for the UPFC. This is what you can do. Then another one, functional control of the shunt converter. So we'll go one by one. So shunt converter. The shunt converter is operated so as to draw a control current ISH from the line. Okay, so shunt, the main, that is what you have. Then one component of this current ISHP, that is real part, is automatically determined by the requirement to balance the real power of this series converter. Then other component ISHQ, that is reactive, can be set to any desired reference level, inductive or capacitive, within the capability of the converter. So capability of converter within that operating range circle. Another point, you have the reactive compensation control mode of shunt converter are very much similar to those commonly employed for statecom and conventional static wire compensator. So it is similar to that part. So now different control mode, functional control mode. One you have is, this is your reactive control mode, that is Q control, controlling of Q. So controlling of P will also be there. So here now you are having is Q control, controlling of Q. So in this mode, the reference input is inductive or capacitive var request as per that. So you can either give inductive or capacitive. The shunt converter control translate the var reference, so either inductive var or capacitive var reference, into the corresponding shunt current and adjust the gating of the converter to establish the desired current. Okay, so this is, so here in this case the reference input you have is inductive or capacitive var. Then this control will actually convert or translate this reference into a corresponding shunt current, so requested shunt current, and adjust the gating of the converter to establish the desired current. So this required for gating signal. Then the control in a closed loop arrangement uses current feedback signals obtained from the output current of the shunt converter to enforce the current reference. So this current reference. Another point, you have feedback signal representing the DC bus voltage. VDC is also used to ensure the necessary of DC link voltage. Okay, so that is whether that requirement, the DC link voltage requirement is there or not, is actually given by that VDC feedback. Say that. Then another one is the most widely used, the automatic voltage control mode, that is there, another mode of functional control of this. So in this voltage control mode, which is actually practical application most widely used, the shunt converter reactive current is automatically regulated. So here ISH is actually automatically regulated to maintain the transmission line voltage to a reference value. Say suppose the reference value say is around 400 kV, then it will automatically regulate to keep within that 400 watt at the point of connection with the defined droop characteristics. So droop means, because as the line is loaded, so what you have droop characteristics means this is at ideal now. Say suppose this one. Now droop means little bit drooping, no? So drop. So this is called as actually droop. So characteristics. So if you see the characteristics of DC generator and AC generator droop pending, so that because of that drop or losses. Yeah, so drooping this is what actually droop characteristics. Droop down. It is drooping down. Then actually the droop factor, the factor actually defines the per unit voltage error per unit of the converter reactive current within the current range of converter. Okay, so droop factor will actually, so higher the droop factor, higher will be the error. Then the automatic voltage control uses voltage signals, feedback signals. In first case, the VAR nadi current feedback signal. No, here it is using the voltage feedback signal. Okay. Then series converter controls the magnitude and angle of voltage vector we inject it in series with the line. So this is what you can have. Then another one is another mode of or controlling the series converter is functional control of series converter. Now you have is direct voltage injection mode. The series converter simply generates the voltage vector VPQ with the magnitude and phase angle requested by the reference input. So this operating mode may be advantage when a separate system of optimization. So optimization or optimization of rating is required. Okay, so then we use this mode, direct voltage injection mode. So here just you can have the special functional case of direct voltage injection includes those having dedicated control objectives. For example, when the injected voltage vector VPQ is kept in phase with the system voltage for voltage magnitude control or in quadrature with it for control quadrature boosting or in quadrature with the line current vector to provide controllable reactive series compensation. So these are the special like cases where you use this direct voltage injection mode. Then you have this bus voltage regulation and control mode. So you are here, what you are doing is you are actually regulating the bus voltage. Okay, so injected is kept in phase with the input bus voltage and its magnitude is controlled to maintain the magnitude output bus voltage vector V2 at the given reference value. So you are controlling the bus voltage here. Then another, so line impedance is actually nothing but this is your similar to that of series compensation line impedance. Okay, so here the magnitude of injected voltage VQ PQ is controlled in proportion to the magnitude of the line current so that the series insertion emulates an impedance when viewed from the line. Okay, so then the desired impedance is specified by the reference input. So this same thing. Yeah, that nothing new, so you can just go through. And last one is PAR, phase angle regulation mode, PAR mode, phase angle. So you are regulating the phase angle to control the functional learning, external control learning. The injected is controlled with respect to the input bus voltage vector V1 so that output bus voltage V2 is phase shifted, means either lag or leak without any magnitude change. So here the magnitude will not be changed, but angle will be changed in phase regulation mode. So quadrature booster that is very. And then last one, another type you have is automatic power flow control mode. So here the power flow is automatically controlled. Okay, so the magnitude and angle is controlled so as to force such a line current that results in desired real and reactive power flow. So here. So here this mode which is not achievable with conventional equipment has so far reaching possibilities for power flow scheduling and management. So this is actually mainly used in this power flow scheduling and then management. Okay, so the power flow and so scheduling and all this thing you might have studied in this, no? The real power flow scheduling and then where you have studied, have you studied or this one?
Yes, sir.
Power flow scheduling.
Power system operation and control.
So there, I think you might have heard that one. So this is how the scheduling is done. So here, the automatic power flow control mode that is there. So UPFC here. Then it can also be used effectively to handle the dynamic system disturbances. Example is to damp out the power oscillation, damping out. So see, now from here, now you can have basic control system for P and Q control, so active and reactive power. So UPFC has many possible operating modes. However, this we are using the automatic power flow control mode, which provides independent real and reactive power in the line we are using. So of many operating possible operating modes, we will be using this automatic power flow control because of the fact that it provides independent control for real and reactive power. Okay, so hereafter whatever we will discuss. So in this control mode, it utilizes most of the unique capability of UPFC, and it is expected to be used as the basic mode in the majority of the practical application, whatever you are using. So this automatic power flow control mode is used. Okay, so accordingly, you can have the block diagram giving greater detail of control schemes are shown for the series converter in this. Or you can see this. So this is for converter can generate output voltage and magnitude at a given DC bus voltage. So block diagram. So here you are giving basic control P and Q. Same thing, you will have P reference, Q reference, V2 is given at computer, so it will compute it, and then you will give this. Right. Then real and reactive compute here, and then sum it there, compare here, and then given to the error amplifier. So then what it will do, error amplifier will actually compare it, and then whatever error is there, it will then neglect it and then give it to the series injected voltage limit. Then after that, V2 PQ and V2 P will be there. Magnitude, and then this magnitude and phase computer will actually calculate this magnitude and phase angle, and then it will give to the, and then the function of this phase lock loop PLL, what it will do is it will generate this theta, angle theta, and this angle theta magnitude of this one is given to the reactive part component is given to this summation, and then it will generate rho compensation angle, and then they are given there, and then this is actually this theta is given to the gating of the gate of the converter, series converter, and then the series converter will ignite, and then it will start injecting the voltage. Okay, so this is what you have. So we'll stop here for today's class.